Hello everyone, this is Chemplified, and in this video we will talk about SN1 reaction, also goes by the name substitution nucleophilic unimolecular reaction. Let's start the video. SN1 mechanism. SN1 stand for unimolecular nucleophilic substitution or substitution nucleophilic unimolecular, both are the same. You can call it by any one of the terms. Now this mechanism involved two steps. So it is a two-step reaction or two-step mechanism, and it follows first order kinetics. I have not written that point, but it follows first order kinetics. And to explain this mechanism, we will consider the hydrolysis of tertiary butyl bromide with aqueous NaOH. If you want to know about SN2, I have already made the video, and you can go to the channel and watch it. So these are some important points about SN1 mechanism. Now let's start with the mechanism. Now the first step 1 is the alkyl halide. In our case, our tertiary butyl bromide. This is our tertiary carbon, 3-degree carbon. The alkyl halide ionizes to give a planar carbonium ion. The carbonium ion is planar because the central positively charged carbon atom is sp2 hybridized. So what this statement is saying is when this bromine atom is removed, as soon as this bromine atom is removed, since bromine is electronegative, it will take the electrons from the bond, right? So carbon is left the carbon is left with one electron short, so carbon will acquire a positive charge. As soon as carbon acquires a positive charge, its hybridization changes to sp2 hybrid, right? sp2 hybridization will be there, and sp2 hybridization is planar in nature, which means all these four carbons are in single plane. Now this has a purpose. So remember that sp2, as soon as bromine atom is removed, the carbocation so formed is sp2 hybrid, right? Now what is the use of this planar carbocation so formed? As soon as the planar carbocation is formed, now this is a positive charge, it needs a nucleophile to attack. In our case, the nucleophile is OH minus ion, which is from NaOH, right? In the first slide we told that tertiary butyl bromide with aqueous NaOH. So the NaOH will provide the OH minus, right? Now the OH will have to attack the carbon. Now since the carbocation formed, the 3-degree carbocation so formed is planar in nature, the OH has the attack possibility from both sides. The OH can attack from this side or from this side, it doesn't matter. After the attack, it will form bond with carbon. So carbon will form bond with oxygen, right? And your reaction is complete. But in what happened in SN2, there will be inversion of configuration. We call it Walden inversion, right? In this case, Walden inversion will not take place. But since there are both possibilities that OH can attack from the left side as well as right side, so there is another possibility of formation of a molecule like this. Now look at this molecule and the above one that I have made recently. In the molecule below, the OH is present on the right side, and the molecule above, the OH is present on the left side. So both are of different configurations, right? And both will be formed. If OH attack from the left side, the above molecule will be formed, and if OH attack from the right side, the below molecule will be formed, right? The molecular formula is same, just the configuration is opposite. But since the configuration is opposite and there is possibility of formation of both these compounds, both these molecules, so you are not going to get a single product in your reaction. You will get a racemic mixture. What you are going to get is racemic mixture, right? So in SN2 mechanism, Walden inversion took place. In SN1, Walden inversion will not take place. Instead, you will get a racemic mixture, which consists of both type of molecule. In one molecule, the OH will be on the left side, and on the other, the OH will be on the right side, right? So that's how it works. Let's move to the next. Now what is the order of reactivity? What is the order of reactivity of haloalkanes towards SN1 reaction? So first of all, remember this order of reactivity. Tertiary carbon is highly reactive towards SN1, then secondary carbon, then primary carbon, and then 0-degree carbon, right? Now why this 3-degree carbon is highly reactive towards SN1 mechanism? If you remember, then in the first step there is formation of carbocation, right? There is formation of carbocation, and the stability of this carbocation formed will decide the fate of the reaction, right? So let's take a look at the order of reactivity once again. Now if this bromine is removed, carbocation is formed. So this is 3 degree carbocation, this is 2 degree carbocation. If this bromine is removed, this is 1 degree carbocation and this is 0 degree carbocation, right? Now which one is most stable? Now if you look closely, this 3 degree or tertiary carbocation is highly stable. Why? Because it consists of 3 alkyl group, and one of the property of alkyl group is to show plus I effect, plus inductive effect. That is, they have the ability to push the electron towards the carbocation, right? And since carbocation, since the central carbon carries a positive charge, to stabilize this positive charge we need some negative charge, and we get the negative charge from electrons. And in this case, in the first case, 3 degree carbocation, the electrons are being pushed toward the central carbon and are able to stabilize the carbocation so formed, right? Now if you look at the secondary carbon, there are only 2 alkyl groups, so they are also pushing the electrons, but the amount of negative charge which is being pushed in 3 degree carbocation is greater than secondary carbocation, and which in turns is greater than primary carbocation, right? So that's why, since all these alkyl groups show plus I effect, the highest plus I effect is shown by tertiary carbocation, and this carbocation is most stable, and this stability will help it to undergo SN1 reaction, right? So if you find a question on order of reactivity of haloalkane towards SN1 reaction, just check the carbocation so formed, whether the carbocation is primary, secondary or tertiary. A 3 degree carbocation will give SN1 reaction more easily than 1 degree carbocation, right? Now 2 degree carbocation is a difficult case, we will discuss it in separate video. 2 degree carbocation, the reactivity of 2 degree carbocation towards SN1 or SN2 depends on various conditions. We will discuss that separately, right? So if somebody asks which one will give SN1 reaction, the tertiary carbocation will give SN1 reaction easily. Now the question arises, why primary alkyl halide do not give SN1 reaction? Now primary alkyl halide simply means as soon as this bromine is removed, carbocation will be formed. This carbocation will be 1 degree carbocation or primary carbocation. Why primary carbocation is not giving SN1 mechanism? Now the reason lies on the stability of carbocation. I will make the complete diagram. Now look at these 3 carbocations. This is 3 degree carbocation, this is 2 degree and this is 1 degree. Now in case of 3 degree carbocation, there are 3 alkyl groups. There are 3 alkyl groups present which are pushing the electron towards the carbon carrying positive charge and hence stabilizing the carbocation. So this carbocation is highly stable, right? In case of secondary, there are only two alkyl group. These two will push the electron towards the central carbon and stabilize the positive charge, but the amount of stability for this carbocation is less than 3 degree. So the order is 3 degree, 2 degree and 1 degree. Higher the stability of carbocation, higher is the possibility to go for SN1 mechanism, right? Since 1 degree carbocation so formed is least stable, 1 degree carbocation least stable in all these 3 cases, hence it will not give SN1 reaction mechanism, right? Why? Because it needs for the reaction to proceed with the SN1 mechanism, there is a need for the formation of carbocation, but that carbocation should be stabilized by some other source, and in this case in 1 degree carbon only one alkyl group is present, hence this is not able to completely stabilize the carbocation so formed. In the end, since this carbocation is not stable, the leaving group can leave and will come back and attach itself again. So in simple terms, the leaving group will not leave easily. That's why primary carbon or primary carbocation will go SN2 mechanism. The primary alkyl halide will go through SN2 mechanism. Some nucleophile will attack from the backside and force the halogen atom to leave, right? That's what happened in case of primary alkyl halide. I hope I am clear. This will be it for today's video. Thank you very much for watching.